Hello and welcome to this GCSE Chemistry exam paper walkthrough for the 2022 AQA Paper 1. During this video, I'll be talking out loud and explaining my reasoning and my thoughts and writing those down in red, and then the answers that are going to get you the marks for the exam questions will be written in purple. Feel free to download the questions from the link in the description, have a go at them yourselves, and then watch this video and see how you got on. This question is about metals and non-metals, and the diagram is showing us an outline of part of the periodic table, and then part A tells us about element Q. We're told it's a dull solid with a melting point of 44 degrees C, and it does not conduct electricity. And we've been asked which section of the periodic table is most likely to contain element Q. Well, the fact that it does not conduct electricity suggests that this will be a non-metal, and this is further backed up by the low melting point and the fact it's not a shiny solid. And so this is going to be a non-metal, and this sort of set of stairs-looking area of the periodic table here, that separates the non-metals in region D from the metals, in fact, in all of those other regions. And so the correct answer is D, because the element is going to be a non-metal, and the right-hand side and the top of the periodic table is where you find the non-metals. And then we're told that element R forms ions with a formula of R2 plus charge and R3 plus charge. And we're asked which section of the periodic table is most likely to contain element R. Well, for triple chemistry, you need to know that elements that can form more than one different charged ion that is positive as well is the transition metals. Normally, the elements, for instance, in group 1 would form a 1 plus ion only, for instance. And so the transition metals is this middle block here between group 2 and group 3. And so B is the correct answer because that is where you find the transition metals. Give two differences between the physical properties of the elements in group 1 and those of the transition elements. Well, the transition elements are in area B of this periodic table, and group 1 is on the left-hand side. That's the alkali metals. So we're comparing those two parts of the periodic table. Additionally, we're comparing the physical properties of these elements. And a physical property is a characteristic of a substance that can be observed or maybe measured without changing that substance's chemical identity. So, for instance, its colour, its density, and its melting point. Whereas in contrast, the chemical properties describe a substance's potential to undergo a chemical change or a reaction by forming new substances. So, for instance, its flammability, its acidity, or maybe how reactive it is with oxygen or water. And so we need to be careful here to talk about physical properties and not get distracted by chemical properties. When we highlight our differences, the easiest thing is to have one of the groups of the periodic table in mind. So, for instance, group 1 as our focus. And so the group 1 elements have lower melting points than the transition elements. And group 1 elements have got lower densities than the transition elements. We could also say that they are softer or they are less strong. We don't need to say all of those. Any two will get us the 2 marks, one for each of our ideas. Complete figure 2 to show the electronic structure of an aluminium atom. Use the periodic table. The electronic structure shows us how many electrons there are in each shell of a particular atom, and the electrons are represented by either dots or crosses. It doesn't matter which, you just choose which you want to do. We've been commanded to use the periodic table. That's to find out how many electrons that we need to draw. Aluminium has got the symbol Al. It's got 2 numbers, 27 and 13. 13 is the atomic or proton number, which means an aluminium atom has got 13 protons, and therefore it will also have 13 electrons. We need to put those 13 electrons into the shells. The first shell can hold a maximum of 2 electrons and then it is full. So once we've placed our 2 electrons in that shell, we need to move out to the next shell. This one has got a capacity of 8. And so 2 and 8 is 10. So we need to fill this shell as well. Once we've put our 10 into those two shells, that means we've got 3 left over. That goes into the next shell. So the outer shell of this element has got 3 electrons in it. And we find aluminium in group 3. Aluminium is a metal. Describe how metals conduct electricity. Answer in terms of electrons. The structure of metals is that they have got regular layers of atoms or ions in 3 dimensions. They're sometimes called a giant metallic lattice. And these ions are so close together, their outer shells overlap, and the electrons in those outer shells become delocalized. And this is where the electrical conductivity comes in, because these delocalized electrons carry charge. They're negatively charged, and they are free to move around through this metal structure. And in fact, they're sometimes referred to as free electrons. And so the movement of these electrons through the metal structure is the electric current. And so for 3 marks, we need to refer to the electrons being delocalized. That's a key word. And the fact that they are carrying charge is very important, and they are free to move through the structure. It's really important to say through the structure rather than throughout, because through gives us this idea of the one direction of electric current, whereas throughout maybe implies some randomness to the movement of the electrons, and they're flowing towards the positive terminal of a power supply. Name the type of bonding in compounds formed between metals and non-metals. This is something that you could just simply remember, but you could also work it out. First of all, metals typically only have a few electrons in their outer shell, and non-metals generally have a almost complete outer shell. And so the way they bond together is they transfer electrons from the metal to the non-metal. And this forms ions, and so the type of bonding is ionic bonding. Then we're told that magnesium oxide is formed from the metal magnesium and the non-metal oxygen. And we've been commanded to describe what happens when a magnesium atom reacts with an oxygen atom. And we've been given the big hint that we need to refer to electrons in our answer. To help you do this question, I recommend that you work out what the electron arrangement is for the magnesium and what it is for the oxygen. And so magnesium has got an atomic number of 12, that means 12 protons and 12 electrons. And so there will be 2 electrons in the first shell, 8 in the second, and 2 in the outer shell. Oxygen has got an atomic number of 8, so it will have 2 electrons in the first shell and 6 in its outer shell. And you can see now that magnesium with 2 in its outer shell needs to get rid of those 2 electrons in order to have a full outer shell. That second shell becomes the outer shell and it will be full. And we can also see that oxygen needs to gain 2 electrons to fill its outer shell, and that will turn the 6 into 8, which is a full outer shell. And so to connect these ideas together, we need to say that the magnesium loses electrons and the oxygen gains electrons. There's a mark for each of those ideas. We also need to recognise that it's not just 1 electron being gained, but actually it's 2 electrons that are being gained by the oxygen and lost by the magnesium. So I'm showing these as separate ideas, but you could actually get all 3 marking points from saying that magnesium loses 2 electrons and oxygen gains those 2 electrons. So the one sentence actually gets you 3 marks. And then to finish off, we've got 4 marks though. And so we need to recognise that once these electrons have been lost and gained, what's left over is an ion. And so magnesium has got 12 protons and 12 electrons before it forms this bond. Once it's formed this bond, it's got 12 protons and 10 electrons. And so the protons are positively charged and the electrons are negatively charged. So that means that the magnesium has got an overall charge of 2+, because there's 2 of those protons that aren't being cancelled out by electrons. And then in the same way, the oxygen has got 8 protons and 8 electrons when it's an atom. Once it's gained those 2 electrons, it's still got 8 protons, but it's now got 10 electrons. And so this gives the oxygen an overall charge of -2. And once we've got atoms that have lost electrons or gained electrons, they actually aren't atoms anymore. They become ions. And so for our 4th mark here, we could say that we form magnesium ions and oxide ions. Or we could actually say what the charges are. So we could say we've got a magnesium 2+ ion and we've got an oxide 2- ion. Note the change in the name, it becomes an oxide ion. And within this, we've got the ionic bond, the attraction between the positive magnesium and the negative oxide ion. And that is the nature of this ionic bond, that electrostatic attraction. Sodium carbonate reacts with hydrochloric acid in an exothermic reaction. That means the temperature will increase during this reaction. The equation for the reaction is Na2CO3 in the solid state, so that will be the sodium carbonate, reacts with the HCl aqueous, 2 moles, and that's a solution, and then it turns into 2NaClAq, also a solution, carbon dioxide gas, and liquid water. A student investigated the effect of changing the mass of sodium carbonate powder, so again we're being told it's a solid, on the highest temperature reached by the reaction mixture. Plan a method to investigate the effect of changing the mass of sodium carbonate powder on the highest temperature reached. Questions like this will always have a banded mark scheme, and so we want to aim for a level 3 answer, which means that we'll be aiming for 5 or 6 marks out of 6. And to get those marks, we need to make sure we're clear about what the question is asking us to do and the experiment it's asking us to plan a method for before structuring our answer. The starting point for this is to unpick key information. We're being told it's an exothermic reaction, so the temperature will increase, and so we're likely to be doing an experiment that measures that temperature increase. And so your brain needs to be thinking, I've done experiments like this using a chemical reaction inside a polystyrene cup, and we have a thermometer to measure that temperature change. We've also been told that we're investigating the effect of changing the mass of sodium carbonate powder. Well, whenever they say that we're changing something, this is the independent variable. And it's the effect on the highest temperature reached. And that will be the dependent variable. And there's obviously a third type of variable, which are control variables. And these are things that we need to keep the same. Mark schemes are quite hard to unpick for questions like this. It's not always obvious how we get the 5 or 6 marks. There are often bits in bold which are identified as key steps, and these must be included in the topped band answer, and that's because the investigation wouldn't work without them. And you can usually score these marks in a brief method, including the essential equipment that you would use. You also need to make sure your experiment would give a valid outcome, so that means that you need to describe or acknowledge the fact that you're kind of being mindful of the key variables in this experiment. So you're describing what you'll change and what you'll measure and what you'll keep the same. So that's those control variables. And you should aim to include 2 control variables as a minimum in your method. Your answer also needs to be logically sequenced. And this doesn't mean that you should write in continuous paragraphs of extended text. You can write in bullet points. In fact, I encourage you to write in bullet points because that makes it easier for the examiner to find out which marks you should be awarded. And so the method that you write needs to tell the story of the steps that you would carry out as you worked your way through this investigation. And so the first thing that you would do is measure the volume of hydrochloric acid that you're going to use with a measuring cylinder to make sure you get the accurate volume. And then you would pour this acid into the polystyrene cup where the chemical reaction was going to take place. And then you would add a known mass of sodium carbonate to the polystyrene cup. and you would have measured this known mass with a balance, and that allows you to know that you're using a particular mass of the sodium carbonate. When referring to the fact that we are measuring particular quantities of solid, we should always say that we are measuring the mass, and if we are measuring a liquid, we should always say that we are measuring the volume of that liquid. And then once you've added your sodium carbonate to the acid, you would need to stir this mixture. And you could achieve that by stirring it with the thermometer that you will use to measure the temperature. And then that would be the next step of this method. You would measure the highest temperature reached with that thermometer that you'd already put in and were using to stir. Now, you could also measure the starting temperature and the finishing temperature in an investigation like this, but you've been commanded to find out the effect of changing the mass on sodium carbonate on the highest temperature reached, not the temperature change. And since we need to know the effect of changing that mass of sodium carbonate, the next thing that we would do is repeat the experiment, and this time we would use a different mass of sodium carbonate. And then again, we would measure that highest temperature reached with this new mass of sodium carbonate. And realistically, to be confident that you've achieved a valid outcome, you would aim to do 5 different masses of sodium carbonate in total. And then, once you've done this experiment once through with your 5 different masses of sodium carbonate, you would repeat the whole investigation again. This would allow you to spot any results that were anomalies. That means that they didn't fit in with the general pattern, and then you could calculate a mean for the highest temperature reached. And then the final step is to acknowledge the control variables. And so these are the variables that you would need to keep the same each time you repeated the experiment, whether that was for the same mass as previously or for a new mass of sodium carbonate. And there are a number of control variables that you should use. The most important 3 are, firstly, the starting temperature of the acid. If you are measuring the highest temperature reached, it's really important to start at the same temperature every time, because that will definitely have an effect on the highest temperature reached. Second, we need to make sure we use the same volume of acid each time we do this experiment, because a different volume of acid, a higher volume for instance, would make a different temperature change occur, probably a higher temperature for a higher volume of acid. And then finally, we need to make sure that we use the same concentration of acid each time we repeat the experiment, because a more concentrated solution of acid is likely to give us a higher temperature change. And so this is more than enough to get us our 6 marks. The 5 key steps are highlighted here. These are non-negotiable. They must be included to get 6 marks out of 6. In addition to that, you should include at least 2 of the control variables, which are the final 3 bullet points, and it's possible that you would need to use 1 or 2 of these extra points as well that I'm showing slightly offset from the others. These are linked ideas rather than absolutely key concepts. And so have in mind that when looking at a mark scheme, you need to include all of the ideas in bold and 2 or 3 of the others, including, for a question like this, the control variables. Figure 1 shows a line of best fit drawn through the student's results. And you can see on the x-axis there is the thing that has been changed, and that is the mass of sodium carbonate in grams. And on the y-axis we have the highest temperature reached by the reaction mixture in degrees C. We have been commanded to determine the gradient of the line of best fit in the figure 1, and we've been commanded to use the equation where the gradient is the change in highest temperature divided by the change in mass, and we have a follow-up command to give the unit. And we've got 5 marks available for this question. When you've got a graph question and you've been commanded to use the particular graph, I would encourage you to get into the habit of annotating that graph and showing the examiner how you've extracted the data from it that you're going to use. Because if you extract the wrong data from the graph, you can still get some credit. And so we're going to be using the equation change in highest temperature divided by change in mass. And so the first things that we need to do are to find the change in the highest temperature and the change in the mass. In order to do this, we need to use the y-axis, and the y-axis goes up in 0.2s for each small square. I know this because the bottom is 20 and we go 10 little squares up, and that is 22. So that is a change of 2 degrees C, but we've had 10 squares to achieve that change. So each square is 0.2. And then for 1 gram of sodium carbonate powder, if we read up to the best fit line and then we read across to the y-axis, we can see we're at 22 and then 1 small square. And so that means we're at 22.2. And then for the maximum for 5 grams, we find 5 grams, we read up to the line, and then we read across, and we get 28 plus 3 little squares, so that is 28.6. And so our temperature change is 28.6 minus 22.2, which gives us 6.4 degrees C as our change in highest temperature. This gets us our first mark. The change in mass is much easier. First of all, we had 1 gram, and then we had 5 grams for the values that I'm using here. And so the change is 5 minus 1, which is 4 grams. That is our second mark. And so to calculate the gradient, we need to take that change in highest temperature, 6.4 degrees C, and divide that by our change in mass, which is 4 grams. And this gets us our third mark for setting out the calculation. It's always important to show your calculations that you're using for any question worth more than 2 marks. And then for our answer, we get 1.6 for our value. That gets us the 4th marking point. And then we've been commanded to give the unit. Now, sometimes the units are things that you just need to remember, but when you're using a graph, you need to think about how you got the value for your gradient. Well, the highest temperature was in degrees C, and we divided that highest temperature by the mass, which was in grams. So we've taken an amount in degrees C and divided it by grams. And so the units are going to be degrees C per gram. But when you write units, you can't leave it like this. It needs to be a single line fraction. And so degrees C per gram needs to have the grams brought up to the same line as the degrees C, and this horizontal line needs to become a forward slash. And so the units for this gradient are degrees C per gram, and you'd write it like this, and this would get you your 5th mark out of 5. The initial temperature for the reaction is where the line of best fit would meet the y-axis. Determine the initial temperature of the reaction mixture. Show your working on figure 1. There are actually 2 different ways that we can answer this question. The first one that I prefer is to take the line of best fit that you've been given and then continue it until you reach the y-axis. This process is called extrapolating. And to do this, you would simply put your ruler and line it up with the best fit line, and then draw an additional line from where the best fit line ends to where the best fit line would meet the y-axis. And when I do this, I get just over 3 little squares above the origin. And so that means that since each little square is worth 0.2, I've got a value of 20.6 degrees C for my extrapolation. So I'd get 1 mark for the extrapolated line, continuing that best fit line along, and 1 mark for my actual value of 20.6. And if you made an error with your extrapolation, but then read off the y-axis value correctly, you would get 1 mark of the 2. The second way to answer this question is to use the gradient that you worked out in the previous question. We got an answer of 1.6 degrees C per gram of sodium carbonate. And this means that for every gram of sodium carbonate that you add, the temperature reached will be higher by 1.6 degrees C. And that works in reverse as well. And so for a 1 gram sample of sodium carbonate, the highest temperature reached was 22.2. And so if we subtract 1.6 from that value, we will get the temperature when we use 0 grams of sodium carbonate. So that means the initial temperature. And so we get an answer of 20.6 this way as well. They have said show you're working on figure 1. And so to do that, you would need to read off the 22.2 value and then subtract 1.6 from it. And that would get you the first marking point. And the second marking point would be the initial temperature. Another student repeated the investigation but added sodium carbonate until the sodium carbonate was in excess. And this is different because the first student added a particular mass of sodium carbonate, measured that highest temperature, and then repeated the whole thing by starting again and adding an entirely different mass of sodium carbonate to an equivalent volume of acid, but fresh acid. This person has taken a particular volume of acid and added more and more and more sodium carbonate to that exact same acid, measuring the highest temperature each time they add a bit more of the sodium carbonate, and then they've kept going until they've got an excess of sodium carbonate. That excess means that all the acid has gone and we're just adding more sodium carbonate to the reacted mixture, fully reacted mixture. And so we've got 3 options here, and we've been asked to pick which sketch graph shows the results obtained when sodium carbonate was added until excess. Option A has a linear relationship, and then the linear relationship continues at a steeper gradient. Option B has a continuous linear relationship throughout, same gradient as the original, give or take. And then the third option is, again, that same linear relationship, but then we reach a point when that relationship completely flattens and the highest temperature reached is constant. And C is actually the correct answer, because what we would expect is the increase in temperature as we add more sodium carbonate, exactly how we found for our reaction for the first student. But once we reach an excess of sodium carbonate, it doesn't matter how much more we add, we will not reach a higher temperature because there is no acid left for that sodium carbonate to react with. And that's why that temperature doesn't change after this point. This point here, whatever that number might be, that is the point where we are adding an excess of sodium carbonate. Figure 2 shows a reaction profile for the reaction of sodium carbonate with hydrochloric acid. And we can see we've got a typical reaction profile here, but they have missed some things out. They've not labelled the y-axis value. They're calling that X. We've got the starting energy of the reactants here, whatever that number might be. They don't ever show numbers on profiles like this, really. And then we've got a curve that goes up to a peak and then down again, and it goes down to the products. And this product's value, as we read across this dashed line, this is the energy that the products have got. And then we've got a line from the reactant's energy to the product's energy, and that's not labelled either. They've just called this Y. And the question is asking us, what do the labels X and Y represent on figure 2? Well, the x-axis is the progress of the reaction. So that is time, really, where here is the beginning of the reaction and here is the end of reaction. So as time goes on, the reaction progresses. And what X is doing is it's showing us how much energy the chemicals have got at different stages in the reaction. Here we've got the reactant's energy, here we've got the product's energy, here we've got the energy increasing as we put the activation energy to make the reaction happen. And so X is simply the energy. That's all you would need to write for that 1 mark. Y is obviously related to that energy. It is going from the reactant's energy level, that is here, and pointing down to the product's energy level, and that's here. And so Y is representing the energy change for those chemicals. And then the final part of this question says, how does the reaction profile show that the reaction is exothermic? Use figure 2. The fact that we're being commanded to use the reaction profile means that we need to answer in terms of energy of the reactants and products and not comment on bonds breaking, which sometimes is a viable answer, but not when we're referring to a reaction profile. So there's two ways that we could answer that. We could first of all say that the energy level of the products is below that of the reactants, and that allows us to tell at a glance that this is exothermic. For endothermic, the products would be higher than the reactants. Alternatively, we could say that the energy of the chemicals is decreasing, and that is distinctive of an exothermic reaction. The chemical energy decreases and the thermal energy is released as a result of that. And so the temperature would increase. Whereas in endothermic, the chemical energy increases and thermal energy therefore goes down and the temperature would drop. This question is about the different forms of carbon. Figure 1 represents the structure of diamond. And there is a key on the right-hand side where we're told that the grey circles are representing the carbon atoms. And if we pick one of the carbon atoms towards the top, we can see that there is a three-dimensional element to this structure where each carbon atom has other atoms bonded to it in a tetrahedral arrangement. We've been asked to describe the structure and bonding of diamond. Well, the structure is what type of substances make up diamond. And there are 4 options that you could have. You could have metallic, ionic, giant covalent, and molecular covalent. And diamond is a giant covalent structure, sometimes referred to as macromolecular. And you could say either of these two things for the first marking point. And so this is the structure of diamond. And then when it comes to the bonding, there are 3 types of bonding that it could be. There is covalent, ionic, and metallic. And everything made from only non-metals will be covalent. And so that means that diamond will be made of a giant structure held together by covalent bonds. And so the covalent bonds would be the second marking point. And then for extra detail, because there are different forms of carbon and diamond is just one of them, we need to enhance our answer by talking about how many covalent bonds there are per carbon atom. And you can see that all of the carbon atoms have got 4 lines coming out of them. And each of these lines are representing a covalent bond. And so that means that each of the carbon atoms have 4 covalent bonds coming out of them. Even the end ones, even though we're not shown all of the carbon atoms that this one is bonded to, we do still see 4 lines coming out of the carbon atom. And so if you see a line in a diagram like this, these are covalent bonds. Explain why diamond has a very high melting point. Well, the melting point for a substance is the temperature at which it changes state from a solid to a liquid. And as a solid, the particles are all very close together and there are strong forces between them holding them in that rigid arrangement. And to change from a solid into a liquid, those forces need to be weakened. And we're being told that diamond has a very high melting point, and so this means that it will not melt until we reach a high temperature, and we need to explain why that is. And so what we need to say first and foremost is that in order to change diamond from a solid into a liquid, we need to break many covalent bonds. And that makes sense because these carbon atoms that we're being shown in the diagram are being held together by covalent bonds. And the only way that we could get those atoms to separate and move more freely is to break those covalent bonds. And so in giant covalent substances, we need to break many covalent bonds in order to change that substance's state. And furthermore, covalent bonds are very strong. And so that means that breaking them is not easy. And so to make that happen, we need to put in a lot of energy to break those strong covalent bonds. And we only have enough energy to make this change happen when the temperature is very high. And that's why diamond has a very high melting point, because it's only when we reach very high temperatures that the atoms have enough energy to break the covalent bonds, holding them together to their neighbouring carbon atoms. Figure 2 represents the molecule C70. And it's a capital C, which means the element will be carbon, and the 70 is referring to the fact that there must be 70 carbon atoms making up the molecule. And we've got a diagram of the molecule here. The grey circles are obviously the carbon atoms, connected by lines which are representing the covalent bonds. And we're being asked, what is the name of this type of molecule? And we've got 4 options. Option 1 is fullerene. And this is in fact the correct answer. C70 is a type of fullerene. It's not the one that you're likely to have been taught. That's likely to have been C60 fullerene, or C60 Buckminster fullerene it's sometimes called. But these two are both spherical, hollow fullerene molecules. Graphene is a decoy. That's a giant covalent structure made up of a single layer of graphite. Nanotubes, or carbon nanotubes, they're sometimes referred to as, they are hollow tube-like structures, or cylindrical structures they're sometimes referred to as. And polymers are very, very large molecules. I'm showing a large molecule here. Polymers really are even larger than this, and they're sometimes represented by their repeat unit inside brackets with an N, showing that this unit inside the brackets repeats many, many times. And so C70 is an example of a spherical fullerene molecule. Molecules such as C70 can be used in medicine to move drugs around the body. Suggest one reason why the C70 molecule is suitable for this use. And we've only got 1 mark here, so therefore it's really important that we do only list 1 reason. Because if we list 2 and the second reason that we give is incorrect, that will invalidate the correct answer. So just 1 answer needed here. I will show you a few of the different options that you could give. First of all, if this medicine is going to move drugs around the body, it needs to be able to carry it somehow. And fullerenes can do this because they are hollow. And this enables them to act as a cage and trap the drug inside it. And so that means that the drug will be either released gradually or not released until it gets to the target area of the body. Additionally, this type of fullerene is unreactive, which means no side reactions will happen inside the body, which would be undesirable. And they're also non-toxic, which means it won't cause harm to the patient taking the medicine. And then one final option that you could give is that this molecule has got a very large surface area to volume ratio, which actually makes it suitable for all manner of different uses, and as a medicine is just one of them. Calculate the number of C70 molecules that can be made from 1 mole of carbon atoms. And we're being told that the Avogadro constant is 6.02 times 10 to the power of 23 per mole. And so that's being very vague because it depends what we're talking about. It might be that many atoms being present in 1 mole of atoms, or in this case, that will be the number of molecules present in a mole of that particular molecule. And this means that a mole is just a word for a number that means a particular amount of substance. And we've been told that we've got 1 mole of carbon atoms. And so carbon atoms have obviously just got the symbol C. And so if we have a 1 mole of carbon atoms, we've got Avogadro's number worth of carbon atoms. And since there are 70 carbon atoms per molecule of C70, and we have 1 mole of carbon atoms, we can work out how many moles of C70 we could build out of that 1 mole of carbon atoms. And to do this, we need to take 1 for the number of moles of carbon and divide it by 70 because each molecule of C70 needs to have 70 carbon atoms in it. And so we could make 0.0142857 moles of C70 out of our 1 mole of carbon atoms. You wouldn't need to include all 6 of those significant figures. I would recommend a minimum of 2 though. And so this will get us our first mark, the number of moles of C70 that we can make. And Avogadro's number tells us that there are 6.02 times 10 to the 23 molecules of C70 per mole of C70. And so what this means then is that we need to take our moles of C70 and multiply it by Avogadro's constant. And structuring it like that will get us the second marking point of the 3. And then the final marking point will be for the actual answer, so that number of molecules of C70, and that will be 8.6 times 10 to the power of 21. There is likely to be a slight variation depending on how much you rounded it earlier on, but if you used those 6 significant figures like I did, you would get 8.6, and it will round to this number as well. This question is about zinc and compounds of zinc. A student produces pure crystals of zinc chloride by reacting zinc oxide with hydrochloric acid. The equation for the reaction is zinc oxide, ZnO, and that's in the solid state, reacts with 2 hydrochloric acid in the aqueous state, so that means the acid will be a solution, and this turns into zinc chloride, that's our target crystals, and they are aqueous, and we also produce water, which is in the liquid state. The student adds zinc oxide to the hydrochloric acid until the zinc oxide is in excess. And excess means that there is more than we need, and there will be some left over. And give one observation that the student could make to show that the zinc oxide is in excess. Well, when the student adds the solid zinc oxide to the hydrochloric acid and then stirs it, that zinc oxide solid will react, and so the solid will no longer be visible. It will be as if the solid has disappeared, but actually it will have reacted. And then they add some more, stir that, and that will react and disappear as well. And they keep going and going and going, and they will know that the zinc oxide is in excess if there is some solid remaining at the bottom of the beaker, or we might say that the solid is no longer disappearing. And so that's what we could say, either of those, for this first mark. In part B, why is excess zinc oxide used rather than excess hydrochloric acid? And this comes down to the state symbols. The zinc oxide is a solid and the hydrochloric acid is aqueous. And the zinc chloride crystals that we are trying to produce is also aqueous. And our choice of chemical for the excess comes down to how easy it will be to remove that excess chemical once the reaction has finished. And if our excess is a solid, like zinc oxide is, it can be filtered out. And so the excess zinc oxide would be caught in the top of the filter paper as a residue, and the zinc chloride solution would collect as a filtrate in the conical flask. And that separation is going to be very easy. And so we could say that the zinc oxide can be filtered off. That would get us the mark. Or we might say that it is easier to remove or separate the zinc oxide. Or we could have the converse and say it is harder to remove the excess hydrochloric acid. As a follow-on for the same reaction, we are asked to name one other compound that the student could add to hydrochloric acid to produce zinc chloride. Well, some things that will react with acids to make salt are metals, metal oxides, metal hydroxides, and metal carbonates. So as a starting point, we've got a list of 4 possible chemicals. Now, we've been told that we are selecting a compound, so that rules out the metal option on this occasion, and we've been asked to name an other compound, and so we're already adding zinc oxide, so that rules out the oxides for our options, and so we could use a metal hydroxide or a metal carbonate. And since we're adding it to hydrochloric acid to produce zinc chloride, we could choose zinc hydroxide or zinc carbonate. Either of those is fine for our 1 mark. And then in part D, we're told that we need to describe how the student could obtain crystals of zinc chloride from the solution of zinc chloride dissolved in water that we would have at the end of the reaction. And this has 2 stages. First of all, we need to heat our solution until crystals start to form. And we would probably do that over a water bath rather than heating the solution directly. Or for this first mark, we could say heat the solution to reduce the volume or to evaporate some of the water. Or maybe we might say heat until the crystallization point has been reached. Any of those 3 options is fine for this first mark. And then our second mark is for saying that we would turn off the heat, we would take our solution and we would leave it to cool or leave it to crystallize. That would get us our second marking point. Zinc chloride is produced in a displacement reaction between zinc and copper chloride solution. And the equation for the reaction is shown here. Zn, which is the zinc, is reacting with our copper chloride, and we are producing zinc chloride and copper. And we've been commanded to complete the ionic equation for this reaction. Ionic equations simplify the overall equation by getting rid of those chemicals from ionic compounds that are not changed during the reaction. And so generally there are fewer chemicals in an ionic equation. And we've got part of the equation already begun. We have the zinc atoms as reactants turning into zinc ions in the 2+ charge. And so what's not mentioned here at all is the copper chloride and the element copper. And I suggest we start with the element copper. Since it is not an ion and not an ionic compound, the copper will be unchanged for the ionic equation. And so we can just write the symbol for copper in this space here. And then when we tackle the ionic compound, copper chloride, we can treat this in a similar way to the zinc chloride. Copper chloride is an ionic compound, and we know that chloride comes from chlorine, which is in group 7, so those chloride ions will have a 1- charge, and we know that there will be 2 of them. And the copper will be a positive ion since it is a metal, and also since it's cancelling out the negative chloride ions. But since there are 2 -1 chloride ions, the copper will need to be a 2+ ion. And that's what we need to put into this space here, copper 2+ charge. And we can see for the ionic equation, the chloride ions are removed because they are not changing. And then we've been asked, why is zinc described as being oxidized in this reaction? Well, in terms of electrons, the acronym oil rig is quite useful because this helps us to remember that oxidation is the loss of electrons and reduction is gain. And since the zinc has gone from atoms of zinc with no charge to zinc ions with a positive charge, this means that the zinc atoms are losing 2 electrons. But actually, it would be okay to just say zinc loses electrons. Zinc and copper can be used with another substance to produce electricity. Complete the figure below to show how zinc, copper and another substance can be used to light a lamp. Label the zinc, label copper, label the other substance used. And we're told that the symbol that's shown here is representing the lamp, and this is the circuit symbol for the component of a lamp, which you should probably recognise from physics. We're being told that the electricity is being produced from a chemical reaction between the zinc and the copper. And so this is a big clue that we must not include a cell or a battery in whatever we draw, because the chemicals are producing the electricity. And when this happens, we call this an electrochemical cell. And to make an electrochemical cell, you need to know that we need to have two electrodes that could take part in the chemical reaction. And so we will need an electrode that is made of zinc and an electrode that is made of copper. And that would be our first marking point here. So right now we've got 1 mark. And since we are using this chemical reaction to light a lamp, this must mean that we have got a completed circuit. And so we need to connect our two electrodes with something that can conduct electricity. And we should know that in cells, what we need to use is an electrolyte. And so our electrodes need to be sticking into some kind of conducting liquid, which is the electrolyte. And this could be an ionic compound which is dissolved in water, which we would call a solution, or it could be an ionic compound that is molten, which means it has been heated to become a liquid. But we would be fine for our second mark just to label the liquid that the electrodes are sticking into as an electrolyte. And then for our third marking point, we just need to make sure that we are using a suitable piece of equipment to contain our electrolyte. And so the best recommendation here is some kind of beaker, or you could have a dish, or I suppose you could have a kind of conical flask. But a beaker is a much easier piece of equipment to fit into this apparatus. And so for our 3 marking points, we need to label the zinc and the copper. We probably don't even need to use the word electrode, but it is a good word to use. And then our solution is the electrolyte, and then the beaker is the container for the 3rd marking point. This question is about groups in the periodic table. The elements in group 1 become more reactive going down the group. Rubidium is below potassium in group 1. Rubidium and potassium are added to water. Predict one observation you would see that shows that rubidium is more reactive than potassium. Observations that we make during a chemical reaction are things that we would notice with our sensors. And when you put the group 1 metals, the alkali metals, in water, they bubble, they possibly catch on fire, they move around, and they might get smaller and smaller and seem to disappear as they react. Now, if we are wanting to show that rubidium is more reactive than potassium, we must use comparative language when describing our observations. For instance, the bubbling might be more vigorous for rubidium, or the flame that we see might be bigger or brighter, or the rubidium might move around on the surface of the water more quickly, it might melt more quickly, or disappear more quickly. Any of these things, absolutely fine for the 1 mark, provided we use comparative language. And then in part B, we are asked to explain why rubidium is more reactive than potassium. Well, the group 1 metals all have got 1 electron in their outer shell, and they need to lose this electron in order to get a full outer shell and become stable. If we take a look at the electronic structure of the first 3 alkali metals, lithium, sodium and potassium, we can see the 1 outer shell electron in each of them, and when this outer shell electron is lost, the penultimate shell, that one that's just inside the outermost shell, becomes the new outer shell, and this is full. And so, if rubidium is more reactive than potassium, it must mean that the outer electron is lost more easily, or that it requires less energy to remove the outer electron. And this is because the atom is larger and has more shells. And so as a result of this, the outer shell electron is further from the nucleus, which is positively charged, and the electrons are negatively charged. And so this means that there is less attraction between that positive nucleus and the outer shell electron, which is negative. And we could also say, instead of that third point, that there is more shielding between the outer shell and the nucleus. And that means that the positive charge of the nucleus is being blocked or shielded by the shells between the outer electron and the nucleus. Complete the equation for the reaction of rubidium with water. You should balance the equation. And currently we've got Rb, which is a symbol for rubidium, reacting with water, H2O, and we are shown that it is turned into two things. We know there must be two things because there are two spaces with a plus between them. And we've got 3 marks, so the first mark will be for the first chemical, the second mark for the second chemical, and the third mark for the balancing. Well, first of all, let's look back at our observations. We see bubbling during this reaction, and bubbling is evidence that a gas is being produced. And in the case of the alkali metals reacting with water, the gas produced will give a squeaky pop when a lit splint is placed near it. And this is because the gas is hydrogen gas. Hydrogen is a diatomic gas, which means it has got the chemical formula H2. And the alkali metals are called the alkali metals because when you react them with water, they produce an alkaline solution. And that means that we're making a metal hydroxide. Any of the alkali metals, when you put it with water, will make a metal hydroxide. And so we're using rubidium here, so that means we need to produce rubidium hydroxide. And it's a group 1 metal, which means it has got a +1 charge as an ion, and the hydroxide ion has a 1- charge. So that means that the formula of rubidium hydroxide is RbOH. And then in terms of balancing, we currently have got 1 rubidium on both sides of the equation, so that is balanced. Hydrogen, we have 2 on the left and 3 on the right, and so that is unbalanced, and the oxygen is 1 and 1. And so we need the hydrogen atoms to be the same on both sides. That is what is stopping this from being balanced. And we have got 2 on the left, which is an even number, and the number that we put in front as a multiplier will always produce an even number. And so actually our big problem is making this even numbers on both sides of the equation. And so the way to do that is to turn the 1 hydrogen in RbOH into 2. And to do that, we need to put the multiplier 2 in front of RbOH, and this solves our hydrogen being odd on the right-hand side, because now we've got 2 times 1 is 2, plus the other 2 makes 4. And so to get us to have 4 hydrogen on the left-hand side as well, we need the multiplier of 2 in front of the H2O. So this has solved our hydrogen problem. And by having a 2 in front of the H2O and the RbOH, it has kept the oxygens as balanced as well, because we now have 2 of each of them. But the 2 in front of the RbOH means we now have 2 atoms of rubidium on the right-hand side, but only 1 on the left-hand side. And so to balance this, we need to put a 2 in front of the Rb on the left-hand side, and now this is a fully balanced equation, with 2, 2, and 2 getting us that third mark out of the 3. And incidentally, this equation is the same as it would be for any of the group 1 metals. All you would do is swap out the symbol Rb for rubidium and substitute in K for potassium, for instance, if it was potassium reacting with water. The noble gases are in group 0, which is a correct statement about the noble gases. The noble gases all have atoms with 8 electrons in the outer shell. This is not correct. Most of them do, but helium, the smallest of the noble gases, only has 2 electrons in its outer shell, and so that is false. The noble gases have boiling points that increase going down the group. This is in fact the true statement. The noble gases have weak forces between these single atoms, and these forces are stronger the larger the atoms are. and as you go down the group, the noble gas atoms get larger, which means their boiling points increase because these forces are larger and the atoms are harder to separate. The noble gases are not molecules with two atoms, they go around as single atoms, so that third one is false, and the noble gases react with metals to form ionic compounds is also false. The noble gases have no reason to react at all because they already have a stable electronic structure because they have a full outer shell of electrons. The table below shows information about the three isotopes of neon. You can see that there are three isotopes of neon, each with three different mass numbers, 20, 21, and 22. And there are abundances of each of them given as a percentage. Mass number 20 has an abundance of 90.48, which means it is the most common, the most abundant of the three isotopes. Mass number 21 is 0.27%. Mass number 22 is 9.25%. And we've been asked to calculate the relative atomic mass, AR, of neon and give our answer to three significant figures. And there's 3 marks up for grabs here, which means the third mark of the 3 is going to be for the correct conversion into 3 significant figures. The relative atomic mass of any atom is the average mass of that atom, taking into account all of the different isotopes that exist for it. And so to calculate the relative atomic mass, you take the sum of all of the abundances multiplied by the mass number for however many isotopes there are for that atom, which is 3 in the case of neon. And then we need to divide that number by the sum of all the abundances, which, when we're working with percentages, is of course 100. And so the AR of neon is 90.48, that's the abundance of the first isotope multiplied by 20, and then add that to 0.27 multiplied by 21, and then add that to 9.25 multiplied by 22. And then we take that number and divide it by the sum of the abundance, which obviously as a percentage is 100. And so we get an answer of 20.1877. Since we've been asked to give this value to 3 significant figures, we need to remove the 877, but the 8 makes us have to round up the previous digit, and so that was a 1, it gets rounded up to 2, and so our final answer is 20.2 to 3 significant figures. This question is about electrolysis. Molten sodium chloride is electrolyzed in an industrial process to produce sodium. The figure below shows a simplified version of the electrolysis cell used. And you can see we have the sodium chloride in its molten state, that means NaCl liquid. And so we're carrying out electrolysis, which means we're working with ionic compounds. And when molten, the sodium chloride liquid splits into sodium ions and chloride ions, which are free to move. We can see that there are positive and negative electrodes in these positions, and the molten sodium is piped off at the top here, and chlorine gas on the left-hand side here. And we've been asked which is the correct half equation for the production of sodium. Now, before we answer this question, we need to remind ourselves that during electrolysis, the ions are attracted to the oppositely charged electrode, and then they move towards it and become discharged. And by discharged, we mean the ions lose their charge, typically turning into elements, and how they do this depends on the charge of the ion. If they are a negative ion, they will lose electrons and become oxidized, or if they are positive ions, they will gain electrons and be reduced. Half equations show half of the picture, either the oxidation or the reduction. And so in terms of seeing which of these is correct, we can actually rule out the first 2 because they are starting with neutral elements and we are producing ions. And that's the opposite of what should be happening. You can see that in the final 2, we start with ions and we finish with neutral element, sodium. So the bottom 2 look pretty good. but one of them is wrong. And the one that is wrong is the one that shows a positive sodium ion losing electrons to become neutral. That's not how it happens. What needs to happen is sodium loses its positive charge by gaining negative electrons and becoming the element sodium. And so the third one here is correct. A mesh is used to keep the products of the electrolysis apart. Suggest one reason why the products of electrolysis must be kept apart. Well, the products of electrolysis are molten sodium, so that is Na liquid, and chlorine gas, Cl2g. Chlorine is a diatomic molecule. And when we're considering why these products must be kept apart, it's worth thinking about flipping that and thinking, what would happen if they were not separated? And sodium and chlorine, if they were not separated, would actually probably react together and reform the sodium chloride in the equation that I'm showing here. 2Na plus Cl2 would react and produce 2NaCl. So we would be putting energy in to carry out this process, but this process would be reversing itself. Which type of particle passes through the mesh in the electrolysis of molten sodium chloride? Well, first of all, we know that the molten sodium can't be passing through the mesh because we're told that the mesh is keeping the products separated. And so that means sodium atoms can't pass through the mesh, so atoms can't pass through the mesh. And similarly, the chlorine gas, which is molecules, can't be passing through the mesh either, so we can rule out molecules as the option. And finally, we can discount the electrons. They are too small and too highly charged to exist by themselves, and they can typically only be shared or transferred. In the very few cases where we get delocalized electrons, this means metals and graphite and graphene, electrons can be free to move, but that's not the case when we've got molten ionic compounds, which is what we've got here. It must be the ions that are free to move through that mesh because the sodium ions need to move towards the negative electrode and the chloride ions need to move towards the positive electrode, so they all need to be able to move across that mesh. Aqueous sodium chloride solution is electrolyzed in a different industrial process. Two gases and an alkaline solution are produced. Which two ions are present in aqueous sodium chloride solution in addition to sodium ions and chloride ions? Aqueous solutions means we've got an ionic compound which is dissolved in water. And so these additional ions come from the water. And water naturally dissociates and produces small quantities of hydrogen ions, H+, and hydroxide ions, OH-. This means that in any aqueous solution, along with the ions from the dissolved ionic compound, there are some hydrogen ions and some hydroxide ions. And so in our sodium chloride solution, we will have sodium ions and chloride ions from the sodium chloride. And in addition to this, we will have hydrogen ions, which we could write as H+ if we prefer. And we will also have hydroxide ions, or we could write OH-. And these ions could be written in either order, 1 mark for each. Name the alkaline solution produced. Well, alkaline solutions typically contain the hydroxide ion, and so it's likely that this solution will be something to do with the hydroxide. But actually, part F asks us to explain how the alkaline solution is produced, referring to the processes taking place at the electrodes. So actually, let's answer this question first and then go back to E. Remember, we've got sodium ions and chloride ions, hydrogen ions and hydroxide ions. So we've got 2 positive ions and 2 negative ions. And in fact, only 1 positive ion will be discharged at the negative electrode and only 1 negative ion discharged at the positive. And you need to remember the rules for working out which ion is discharged. And at the negative electrode, the positive ion from the less reactive element is the one that is discharged. And this is because the less reactive substance forms its ions less readily by losing electrons, and therefore it will more easily gain electrons and turn back into the element. And since sodium is more reactive than hydrogen, the hydrogen ion is the ion of the less reactive element, and so that means that it will be discharged at the negative electrode by gaining electrons and being reduced. And the equation for this is shown here. It's not essential for this first mark. 2H plus gains 2 electrons and becomes H2. And so we'd see bubbling at the negative electrode. And then for the second mark, we need to consider the negative ion. The rule here is that if we have a negative halide ion, then we will get a halogen produced at the positive electrode. And if we didn't, we would get oxygen being produced. But we do have a halide ion here, so it will be the chloride ion that moves across to the positive electrode, where it will lose its electrons and it will be oxidized, which means that the chloride ions are discharged and chlorine is produced. And so the equation for this, the half equation for this, is 2Cl minus turns into Cl2 plus 2 electrons. And so you can see we've got a neutral diatomic molecule of chlorine produced at the positive electrode. And again, we would see bubbling. And then finally, the sodium ions, Na+, and the hydroxide ions, OH-, are left behind in solution and they are not discharged. And that's actually what we need to say for the third mark for explaining the formation of the alkaline solution. But then if we go back to E, we can see that this alkaline solution must be NaOH, or in other words, to name it, it must be sodium hydroxide. And so we would get 1 mark for E for naming sodium hydroxide and 3 marks for F for explaining how this sodium hydroxide solution was produced. 1 mark for each of my 3 bullet points that I'm showing separated out here. This question is about silicon and compounds of silicon. The reactivity series sometimes includes non-metals such as carbon, hydrogen, and silicon. Silicon can be extracted by reducing silicon dioxide with different substances, and the equation for one possible reaction is shown here, where 2 carbon in the solid state reacts with silicon dioxide in the solid state and produces silicon in the solid state and 2 carbon monoxide in the gas state. And we've been asked to explain what this reaction shows about the position of silicon in the reactivity series. Now, you aren't taught about silicon extraction, but you do need to know about metal extraction, and the same rules apply. Firstly, that the reactivity series lists the elements in order of most reactive at the top of the series and least reactive at the bottom. And reduction, one of the meanings of a reduction reaction is the removal of oxygen from a compound. And one of the ways that we can carry this out is by a displacement reaction, and that is where a more reactive element takes the place of a less reactive element in a compound. And you can see from the equation that we've been given at the beginning, the silicon dioxide is silicon bonded with oxygen, but at the end it is converted into silicon by itself. So it has had the oxygen removed, it has been reduced. And the carbon must be the reducing agent because at the beginning it is by itself, but at the end it has got the oxygen that it has removed from the silicon. And what this is proving is that the carbon is displacing the silicon from the silicon dioxide. It is bonded to oxygen at the end and silicon is not. And this must be because carbon is more reactive than the silicon. Or we could say silicon is less reactive than carbon, or alternatively, we could say that carbon is above silicon in the reactivity series. 1 mark for the carbon displacing the silicon, and 1 mark for commenting on their relative positions in the reactivity series, or their relative reactivity. Aluminium also reduces silicon dioxide. Carbon is used rather than aluminium to reduce silicon dioxide because carbon is cheaper than aluminium. Carbon can be obtained by heating coal, and aluminium is obtained from aluminium oxide. Explain why aluminium is more expensive than carbon. So heating coal to produce carbon will require some energy. However, aluminium is obtained by electrolysis from aluminium oxide. And this is needed because aluminium is more reactive than carbon, so cannot be obtained by reduction from that method. And in electrolysis, we need to melt the aluminium oxide at high temperatures in an electrolysis cell, and then supply a large amount of energy continuously and separate out the aluminium from the oxygen. And so this is obviously going to be expensive, but we've been asked to explain why aluminium is more expensive than carbon. And so the presence of that word more in our question means we need to use comparative language, not just say that it is expensive, but say that it is more expensive. And the reason why it is more expensive is that more energy is needed. So not just a lot of energy or a great deal of energy, we need to be comparative, much more energy is needed. And that gets us our second mark after saying that electrolysis is needed to extract the aluminium, and that would be our first mark. Magnesium also reduces silicon dioxide, and the equation for the reaction is 2Mg solid plus SiO2 solid turns into Si solid and 2MgO solid. And so this is very similar to the previous question where carbon was used to remove the oxygen from the silicon dioxide. And we've been asked to give one reason why the products are difficult to separate if magnesium is used to reduce the silicon dioxide. And that's implying that this difficulty wasn't present when we were using carbon to extract the silicon. And when we look at the product, we see that we produce silicon in the solid state, just like in the carbon equation, and we produce magnesium oxide in the solid state, whereas when we used carbon, we produced carbon monoxide, which was a gas. And so the difficulty arises in this case because both of our products are a solid. And that means, how do we separate one solid from another? It's far easier to allow the products to naturally separate when one of them is a gas, because that gas will just leave the reaction mixture and the silicon will be present by itself. But when we use magnesium, both of the products are a solid. Silicon can be extracted by reducing silicon dioxide with different substances. The equation for one possible reaction is 2Mg solid reacts with SiO2, also solid, and produces silicon in the solid state and also 2-magnesium oxide in the solid state. Calculate the minimum mass in grams of magnesium needed to completely reduce 1.2 kilograms of silicon dioxide. And we're presented with some relative atomic mass values as well, which we don't need to look for in the periodic table. There's two possible methods for doing this. Both obviously get us the right answer. I will do them both side by side, writing one of them in the main answer space, and that will be my preferred method, and I'll show the alternative method on the right-hand side. My preferred method has us setting it out as if there was a grid there. And there are 5 rows to my grid, with chemicals being the top row. And the chemicals of interest are magnesium, because that's what we've been asked to find the mass of, and silicon dioxide, because that is the thing that we've been given the mass for. And then the second row is mass in grams, the third is relative formula mass, the fourth is moles, and the fifth is the ratio which we get from the equation. The first thing that we need to do is recognise that when working with mass, mR and moles, our masses need to be in grams, and that suits us well because that is what our final answer needs to be in. And so we've been given 1.2 kilograms of silicon dioxide. We need to convert that into grams. A kilogram is 1,000 grams, so it's 1,000 times bigger than a gram. So we need to multiply our mass in kilograms by 1,000, and we get 1,200 grams. And that would be our first mark out of 5. And then we need to calculate the relative formula mass of silicon dioxide. And to do that, we take silicon, 28, and we add it to 2 lots of 16, because the formula is SiO2, and that little 2 belongs to the element that just went before it, which is the oxygen. So 28 plus 16 gives us 60 as our MR of silicon dioxide. And that gets us our second marking point. And then for the third mark, we need to work out the moles of silicon dioxide. And to do that, we need to use the relationship mass equals MR multiplied by moles. And so when we substitute those values in, we get 1200 grams equals 60 multiplied by moles. And then we rearrange this to find the moles of silicon dioxide, and we get 1200 divided by 60, which gives us 20 moles of silicon dioxide. And then for the fourth mark, we need to work out the moles of magnesium, which would precisely react with 20 moles of silicon dioxide. And to do this, we need to return to the chemical equation. We can see from the chemical equation that 2 moles of magnesium react with 1 mole of silicon dioxide. Or in other words, however many moles of silicon dioxide we are using, we will need twice the number of moles for magnesium. And so what we need to do here is take the moles of silicon dioxide and multiply it by 2. And this gives us 40 moles of magnesium. And then for the final mark, we need to work out what mass this number of moles of magnesium will have. And so again, we need to return to the mass equals relative formula mass multiplied by moles equation. This time we're using it in its more straightforward form, because the mass of magnesium is what we want to work out, and this is 24 multiplied by 40, which gives us 960 grams of magnesium. And this would be our final mark out of the 5. And so you can see both of my 2 methods get you the same answer. The one that I've chosen to show, the grid method, that gives us perhaps some nicer structure, which allows us to work out what to do next after each individual step along the way. And what you can see is we are working our way down the column for one of the chemicals, and then across to the column for the other chemical, and then back up the column for our unknown mass. Si2H6 is a covalent compound of silicon and hydrogen. Complete the figure below to show the outer shell electrons in a molecule of Si2H6. And you can see that we've got some element symbols in this space here, and the electron shells are currently shown as empty circles. Covalent bonding occurs when non-metal atoms bond together by sharing pairs of electrons. And this produces a type of structure referred to as simple molecular, and the particles in this structure are molecules. These can be represented as a displayed formula like I'm showing here, where the lines are representing a covalent bond, or as dot and cross diagrams, which is what we've been requested to show here. And typically the electrons are represented as crosses or dots. We might also use circles or little letter E's, but I'm going to use crosses and dots. So everywhere electron shells overlap is a covalent bond. And this is typically a single covalent bond. And I'm showing single covalent bonds here with a single line. Since silicon is in group 4 of the periodic table, it will have 4 outer shell electrons, and I will show these as 4 crosses. And I'll do the silicon on the right hand side first. It's got 4 overlaps with 4 other atoms, so I will put 1 cross into each space where there is an overlap of electron shells. And then the silicon on the left needs to be treated in the same way. It has also got 4 overlaps, which means it's got 4 covalent bonds. And you can see in the space where the 2 silicon atoms are meeting, in this overlap region here, I have got 2 crosses. This is the single covalent bond between those 2 silicon atoms. And then where each of those 6 hydrogen atoms meets the silicon, we need to put a dot. And so each one of these 6 spaces is a covalent bond with a dot and a cross, or 2 crosses in the case of this one in the middle. And this is what we need to do to get the single mark. We could use all crosses or all dots, but typically we'll use a dot to represent the electrons from one atom and a cross to represent the electrons from another type of atom. Si2H6 reacts with oxygen, and the equation for the reaction is 2Si2H6 in the gas state, reacts with 7O2 in the gas state, and produces 4SiO2 solid plus 6H2O gas. And we're told 30 cm cubed of Si2H6 is reacted with 150 cm cubed, which is an excess of oxygen. And we've been asked to calculate the total volume of gases present after the reaction, and we're told that all volumes of gases are measured at the same temperature and pressure. And we've got 4 marks for this question. If we deal with that final sentence first, since we're talking about the same temperature and pressure, we need to remember that 1 mole of any gas will occupy the same volume as any other gas at the same temperature and pressure. And remember that at room temperature and pressure, this volume is 24 decimeters cubed. And this means that the volume of any gas is equal to its number of moles multiplied by 24, if we're talking about room temperature and pressure. Now, we've not been asked to calculate anything to do with moles here, but we do need to use this relationship, but we can use it in a more simple form, whereby the volume of any gas will be proportional to the number of moles of gas. And this is really important when working with mole ratios from the equation. So we've been asked to work out the total volume of gases present after the reaction. And the total volume will be the volume of gases produced and any gases left over. We've been told that the oxygen is present in excess, which means there will be some oxygen left over at the end of the reaction, and all of the Si2H6 will therefore be used up. And the way that we unlock this question is by looking at the ratio from the equation. We're shown here that 2 Si2H6 reacts with 7O2. And to turn that into the language of moles, this means 2 moles of Si2H6 will react with 7 moles of oxygen. Or to turn it into volume, 2 cm cubed will react with 7 cm cubed of oxygen. And this is because volume is proportional to moles. To put this another way, whatever the moles or whatever the volume we have of Si2H6, it will require 3.5 times the number of moles or cm cubed to react with it. And we've been told we've got 30 cm cubed of Si2H6, and so it will react with some of the oxygen, and we can work out how much by multiplying the volume of Si2H6 by 3.5, and this gets us 105 cm cubed of oxygen used. And the ratio of volumes, 30 to 105, is the same as the ratio from the equation, 2 to 7, just scaled up 15 times. 105 cm cubed of oxygen are used up, and this will get us our first mark, but some of our oxygen will be left over, and we can work out the volume that will be left over by subtracting 105 away from that starting volume of 150, and this means 45 cm cubed of oxygen will be left at the end of the reaction, and this gets us our second mark. To work out the volume of gas produced, we need to look at our 2 products. The water is shown as being a gas, and the SiO2 is shown as being a solid. And so that means we can ignore the silicon dioxide from now on, because we are only concerned with the products that are gases. And water has a 6 in front of it in the equation. So that means 2 moles of Si2H6 would produce 6 moles of water, or 2 cm cubed of Si2H6 would produce 6 cm cubed of water. Or to put it in a more easy ratio, the ratio is 2 to 6, or reduced down, 1 to 3. So whatever volume of Si2H6 we use, we will produce 3 times the volume of water. And since we're using up all of our 30 cm cubed of Si2H6, the volume of water produced will be 30 multiplied by 3, which is 90 cm cubed of water. And then the final task is to work out the total volume at the end of the reaction. So we take our 45 cm cubed of oxygen that was left over, and we add that to the 90 cm cubed of water vapour that was produced, and we get a final volume of 135 cm cubed. And this is our final mark of the 4. This question is about acids and alkalis. Explain why the pH of an acid depends on the strength of the acid and the concentration of the acid. And we have 4 marks available for this question. The pH scale ranges between 0 and 14, with 7 in the middle being neutral, and acids having a pH less than 7, and alkalis having a pH greater than 7. And the pH value depends on the hydrogen ion concentration. And the higher the hydrogen ion concentration, the lower the pH will be, and the further to the left we will move. And in fact, it's a logarithmic scale, which means every pH value change of 1 is actually a 10 times greater hydrogen ion concentration. But that's probably a bit deeper than we need to go for this question. This question is asking us about the strength of the acid and the concentration of the acid. The strength of an acid or an alkali is in fact related to the extent of ionization of the molecule in solution. And so this means if we took an acid, for instance hydrochloric acid, it would ionize if we put it into water. And that means it would dissociate and fall apart into its component ions. And hydrochloric acid would dissociate into hydrogen ions and chloride ions. And all acids produce hydrogen ions. And the stronger the acid is, the greater the ionization will be. In other words, we will produce more hydrogen ions, and therefore we will have a greater hydrogen ion concentration. And so therefore, the stronger the acid, the lower the pH value of the solution. Concentration is related to the number of particles per unit volume, where a higher concentration has a greater number of particles per unit volume. And you can see that I'm showing that with my 2 diagrams here. The one on the left is shown with 5 particles in this volume, and the one on the right, which has got the same volume, has actually got 15 particles. So it's actually got 3 times the concentration as the one on the left. And for an acid, the higher the concentration of acid, we can say specifically the more acid we will have in the same volume. And when you've got a higher concentration of acid, these greater number of acid particles will dissociate and ionize, and we will result in having a greater hydrogen ion concentration, and that will therefore mean that we have got a lower pH for our acid. You can see I've written 6 bullet points here. We wouldn't need to say all of them for our 4 marks. It's to do with the coherency of our explanation overall. As a bare minimum, we would need to say one of the bullet points from each of my 3 sections. My preferred numbers would be to have both of the first 2 and then to say the second in each of my pairs if you only wanted to remember 4 of these 6 bullet points. A student titrated 25 cubic centimetres of hydrochloric acid with 0.1 moles per decimetre cubed barium hydroxide solution. This means that they would have put the hydrochloric acid into a conical flask with 4 or 5 drops of a suitable indicator, and the barium hydroxide would be in a burette above the conical flask. The table below shows the results. We can see that we've got 5 different titrations carried out, and the volume of barium hydroxide solution used each time to make the indicator change colour is shown in each case. The student calculated the volume of barium hydroxide solution to be used in the titration as 23.50 cm cubed. And we've been commanded to explain why the student used a volume of 23.5 cm cubed of barium hydroxide solution. When you analyse the results of a titration, you need to look for the titration results that agree with each other, and these titrations are referred to as concordant. And concordant values are values that are within 0.1 cm cubed of each other. And this first one is much higher than the other four. Typically, the first one that you do is a rough titration, usually larger than the others, and that's the case here. Numbers 2, 3, 4, and 5 are all concordant because they are all within 0.1 of each other. The smallest and the largest has a range of 0.1. And so what you do is you work out a mean titration value by adding up all four of those numbers and dividing it by the number that there are, making sure you get rid of any anomalies, any results that are not concordant. And that's how we arrived at 23.5 in this case. 25 cubic centimetres of hydrochloric acid reacted with 23.5 cubic centimetres of 0.1 moles per decimetre cubed barium hydroxide solution. And the 25 cm cubed of hydrochloric acid will have been measured with a pipette and put into the conical flask with some indicator, and the barium hydroxide must have been in the burette and added from the burette to the conical flask with thorough mixing. And we know that it must be this way around because the volume of barium hydroxide is very precisely 23.5, and we need to use a burette in order to measure that specific volume accurately. And the equation for the reaction is 2HCl reacts with 1 barium hydroxide. It doesn't show us the 1, but there's no number, so we know it's a 1. And it turns into BaCl2 plus 2H2O. And we've been asked to calculate the concentration of the hydrochloric acid in moles per decimetre cubed. When working with solutions in titration analysis like this, we need to always use the relationship moles of solution is equal to concentration multiplied by volume. And those volumes need to be in dm cubed. And so my advice would be, where we've been given volumes in cm cubed, we convert both of them into dm cubed by dividing by 1000. And we need to also note the fact that our concentration for the hydrochloric acid that we're being asked to calculate is in moles per decimetre cubed. And that tells us that the final thing we need to do is take the moles of hydrochloric acid and divide it by the dm cubed of hydrochloric acid. In other words, its volume. And titration analysis always follows the same 3 steps. In step 1, you work out the moles of the first chemical, and that chemical is the one that you know the concentration on the volume for. And then in step 2, you work out the moles of the second chemical by using the ratio from the equation. And then in the final step, you work out the concentration of this second chemical by taking the moles and dividing it by its volume. And so for us here, we know the concentration and the volume of the barium hydroxide added from the burette. And so this is chemical number 1. And so we work out the moles of barium hydroxide by taking its concentration, 0.1, and multiplying it by its volume in dm cubed, 0.0235, and we get 0.00235 moles of barium hydroxide. And then for step 2, we need to look at the ratio. 2HCl react with 1 barium hydroxide. And this tells us however many moles of barium hydroxide we're using, we will need twice the number of moles of hydrochloric acid. And so what we need to do is take the moles of barium hydroxide that we calculated in step 1 and simply multiply it by 2. And so this gets us 0.0047 moles of HCl present in that conical flask. And then when we're finding the concentration of HCl, we are again using moles equals concentration multiplied by volume in dm cubed. And so if we substitute in the numbers that we know, the moles of HCl is 0.0047, and that is equal to the concentration, which is what we're trying to find out, multiplied by the volume in dm cubed, which is 0.025. And so therefore we can rearrange this expression to get the HCl concentration as being equal to 0.0047 divided by 0.025, which gives us a final concentration of hydrochloric acid of 0.188. We would get 1 mark for the moles of barium hydroxide, 1 mark for the moles of HCl, 1 mark for the concentration expression set out, and the final mark for the concentration of hydrochloric acid. And if we made the mistake somewhere along the way, we would get what's called error carried forward if we'd used an incorrect value correctly at a later stage. Another student titrated sulfuric acid with barium hydroxide solution, and the equation for the reaction is H2SO4, aqueous, plus barium hydroxide, aqueous, reacts to produce BaSO4, solid, plus H2O, liquid. And the student measured the electrical conductivity of the mixture during the titration. And we're told that the better a conductor is, the higher the electrical conductivity value. And the results are shown in a graph here. We've got the volume of barium hydroxide solution that has been added in cm cubed, and the electrical conductivity in arbitrary units is shown on the y-axis here. And we've been asked to explain why the electrical conductivity of the mixture was 0 when the sulfuric acid had just been neutralised. And we've been asked to use the equation for the reaction for our answer, and we've been asked to refer to ions in our answer. Well, I think that the best way to explain why the mixture's conductivity has dropped to 0 is to first look at why it wasn't 0 at first. Because we are working with solutions, we need to recognise that aqueous solutions are actually made up from ionic compounds that have ionised when you put them into water and they dissolve. And so in aqueous solutions, the ions are free to move and they move through the solution and they carry charge when they do so. So H2SO4 is made up of the ions hydrogen, 2 of them, and SO4, 2-. And so these will have been in the solution at first. And then at the point of mixing, we would also have had barium ions and hydroxide ions. So all of these ions would be free to move through the solution and carry charge. But when they start to react together, the hydrogen ions will react with the hydroxide ions and they will produce water. And water is a covalent substance. It's made up of molecules, and so it has no charge. And the barium ions will react with the sulfate ions and produce a solid, which will look like a white precipitate that forms during this titration. And this means that we've made an insoluble solid. So as a result of these two reactions, there are no ions in this solution that are free to move around. The only ions that are in fact present are in the barium sulfate, and they are trapped as a solid BaSO4 white precipitate. And then the final part of this question says that the student added a further 10 cm cubed of barium hydroxide solution, and the electrical conductivity of the mixture increased again. Give one reason why. Well, we said that at the point of neutralisation, all of the ions from the acid had been precisely neutralised by all of the ions from the hydroxide, whereas now we have an excess of barium hydroxide solution, and this solution contains ions. And so specifically, our mixture will now have barium ions and hydroxide ions that are free to move through this solution and carry charge. Okay, that's the end of this video. Thanks for listening.